Hello, this is Mr. Collier, and today we're doing the derivative, also called the gradient function. So if you look at this function here, it looks like a parabola. It hasn't got one slope like a line does. A line has a constant rise over run, a constant rate of change. But a parabola does not. It keeps changing. It keeps getting the rate of changes, or the slopes of the tangent lines here are going to get steeper and steeper and steeper. And if you look at the graph here, there's one place where the slope of the tangent line would be 0. We get a slope right there. Over on the right, we get some positive numbers, maybe positive 1, and then somewhere along here we have 2. On the left, we have negative numbers like negative 1 and so forth. So the derivative is is equal to the gradient of a function, and we're going to see how to calculate the derivative in a second. But let's just logically get the graph of the derivative from the original function. So we know the derivative here is 0. The derivative here somewhere is 1. Then we have 2. And to the left, we're going to have negative values. So this is going to be the graph of the derivative of a quadratic. So quadratic is something like, y equals x squared. This one's plus something, but when we have y equals x squared, we get a derivative which is linear. So quadratic to linear. Next one looks like a cubic function, and the graph of the derivative is going to be quadratic. So let's look at where the tangent lines are equal to, or the slope of the tangent lines are equal to 0. We're at these 2 points. So our derivative is going to be here, and here the tangent lines are going to be negative. Okay, negative, so we're going to be pointing down like this. Over here and here, they're positive. So our blue function, the derivative, has to be positive on this side, and then it has to be negative, and then it becomes positive again. So there's the derivative, and one notation to note the derivative is f with a quotation mark of x, or dy dx is the other notation. They both mean the derivative, which is equal to the gradient of a function at any point. Here we have a linear function, and the slope is a number like maybe 3 or 4. It's a constant slope, so the derivative is always constant as well. So that's just a horizontal line. So that's what the derivative looks like here. Here we have another cubic, so it's very similar to before. We're going to have tangent lines are, slope is 0 here and here. So you're going to get another quadratic for the derivative. Okay, so it's all about the tangent line. When a function is increasing, the slope of the tangent is positive, as you can see in the picture. When it's decreasing, it is negative. Another way to say that is f prime of x is greater than 0. F prime of x is less than 0. At an extremum, that means a maximum or a minimum, then the slope is 0. Okay, so we can use calculus to help us find where a function is increasing, decreasing, or where there's a maximum or minimum. You can think of the derivative as the instantaneous rate of change at a point. Okay, so let's look at the next page here, and to find the derivative of a x to the power of n, and n could be positive, negative, could even be a fraction, we always do this little rule right here. This is a rule for getting the derivative of some regular polynomial functions. So notice the n comes down in front of the coefficient, and you reduce the exponent by 1. So that's the basic rule. So let's look at all these functions. In the first one, the derivative, and we'll denote it f prime of x. The exponent gets multiplied by the front coefficient. It's 4. X, reduce the exponent by 1. Next, g prime of x. You're going to do 3, and then there's a 5 in front, so 3 times 5 is 15. And then reduce the exponent by 1. C prime of x, 2 times 2 is 4. Reduce the exponent by 1. Now here you have a 1. It's like 3x to the power of 1. 1 times 3 is 3. And reduce the exponent by 1, you get x to the power of 0, which is just 1. So we leave that. And if you got just a constant, well, constant doesn't change at all, so it this will give you 0. Another way to write that is it's like x to the power of 0, and 0 times this term is 0. So all constants are just the derivative of all constants is just 0. So f prime of x, we bring the 3 down, it's 3x squared, and here this becomes 2. And the second part of the question is find the gradient of the tangent at the point where x equals 2. Okay, so let's do that. At x equals 2, we just substitute in 2 to get the slope at this point. 4 times 2 cubed, and that is 32. Okay, so that's the slope at this particular point. The graph of y equals x cubed, or x to the power 4, I'm going to graph it over here, is kind of like a parabola, but it's a bit fat on the bottom. Okay, but apparently at x equals 2, when x equals 2, then the slope of the tangent is 32. Okay, next, let's plug in 2 into this next one, and we get 15 times 2 squared, 60. Substitute 2 in this one, and we get 8 plus 3 is 11. So the slope here is going to be 11. And the last one, we get 3 times 2 squared plus 2. It is 14. Okay, so notice we've just had some helpful derivatives to remember. For any constant, the derivative is 0. And for ax, the derivative is a. Okay, so the exponent of x can be negative. Now, if you have an x in the denominator, you could always write it as a negative exponent, and then you can find the derivative. So let's take a look at this function. This function you can rewrite as 2x to the power negative 1 plus x. And then when we find the derivative, we get negative 2x to the negative 2 plus 1, which you can rewrite as negative 2 over x squared plus 1. Okay, next one we can write as 3x to the power negative 2, and when we get the derivative, you do the negative 2 times 3 is negative 6, and then we get x to the power negative 3, which you can rewrite as, now that's a negative exponent, so you can write it in the denominator. Okay, so these other ones work similarly. C prime of, well, x was, first of all, let's rewrite c of x. This is 4x to the negative 5 plus 8. And then when we get the derivative, the negative 5 gets multiplied by the 4. We get negative 20 x to the negative 6. And the derivative of a constant is 0. And this derivative you can write as negative 20 over x to the power 6. This function is x to the power negative 1 plus 2 minus 4x to the negative 2 minus x. That's just rewriting the original function. Now we take the derivative, we have to write this notation. So negative 1 times that is negative x to the power negative 2. Derivative of a constant is 0. Next we have negative 2 times negative 4 is positive 8. Reduce the exponent by 1. So that's negative 2 minus 1 is going to be negative 3, and this is going to be just a negative 1. And you can rewrite this as negative 1 over x squared plus 8 over x cubed minus 1.